This is chemistry, and we are answering some questions on units and measurements and also stoichiometry. The first question says, evaluate each of the following and write the answer to the appropriate number of significant figures. Now, these questions might seem so useless here, and I always encourage people that there is no sure way to learn to know that you have learned something except you can go in past papers. You check through papers and then you can determine that I can answer questions. That should have been is it a 2021 paper chemistry? If you check it, the very first question was about these questions that you can see here. They just gave a question like that, add. And people thought, this is so easy. And I was seeing those who were marked. Literally, they failed because they don't understand the rules. It's not just you adding and then you forget. There are rules of addition, rules of multiplication, subtraction, and division. So that is what they want you to understand. Because who would give you this kind of question in chemistry and then just expect you to write it like that? Are you a grade 10? You see? Yeah, that's not the issue. The issue is, do you know the rules that pertain to addition, subtraction, multiplication, and division with regard to the topic? All right, so here we have been given 212.2. And by the way, chemistry use a calculator. So you just punch this on your calculator. 212.2 plus 26.7 plus 402.09. So that has given me 400, oh sorry, 640.99. Now the rule that they want you to know is that when you add or subtract, okay, it's a rule. So after addition or subtraction, what should you know? The final answer must be expressed. Final answer is expressed to lowest number of decimal places. That's a rule. Okay. So you look at the numbers that we are adding. The first number add one decimal place. Second number has got one decimal place. The third number has two decimal places. So the final answer should have one decimal place. That's the meaning. So in other words, this if you write this answer that is yes, not correct because one has got two decimal places. So we just want one decimal place. So that tells you that you have to round off. So we're gonna remove a 1 from 9 and put it on this 9. That is gonna give you a 10. But we don't write tens. So you get it, that 10. You remove that 1 and go and put it on the 0. So the answer that you want is actually 641.0. If you write 641, that is not correct because you're not following the rule. Okay, write one decimal place, and that's the rule. I hope we've gotten it. Is there anyone that is behind? Anyone that is behind? I'll mention it again. It might seem a useless rule, just like most of you thought you could have written, because I remember when I taught you units and measurements, I gave you a quiz for adding, and people sent answers and they didn't even get them correct. And I'll send it again after this class so that you attempt it again. We see now if you'll be able to answer. All right. So that is it for that first question. The next one, we want to also to find this one. You can see what we have. 1.646 times 10 to the power 3. So again, we'll just work them out the way they are. So 1.646 times 10 to the power 3 minus we have got 2.18 times 10 to the power 2, and then okay, we have got, I want you to notice that, can you see that these guys here are in brackets? I hope you can tell. So with a rule is brackets off. Remember the board mass? Board mass, it says that brackets off, you do the division and the multiplication and then the addition and subtraction. Okay, so first here, I've added these first two. Those ones, I've added them. I'm going to write the answer. So for these first two, after adding them, I've gotten a 1.428 times 10 to the power 3. And then we have got a plus. We are going to work out what is in the brackets. So that is 11.36 times 10 to the power 4 multiplied by, okay, multiplied by 5.17 by 10 to the power negative 2. And that one has given me 5.87312 times 10 to the power 3. Okay, so this is this part, right? After I do this, then I'm gonna now add these two. So the answer that I have here, plus 1.428 times 10 to the power that. So that is given me a 7.30112 times 10 to the power 3. So what is the rule again? Remember, we are also adding and subtracting. So the same rule applies. Okay, apply the rule as on top. So we just need to have on our numbers, this was 3 decimal places, 2 decimal places. So I'm gonna write, okay, let me just point at it so that you'll be able to see. This one is 3 decimal places. This number is 2 decimal places. So for these ones which we are multiplying, this is 2 decimal places. And then this guy here was also 2 decimal places. So the final answer, anyone to tell me what should be the final answer? How many decimal places should it have? Because this was addition. Anyone? Very good. Okay, so final answer expressed to 2 decimal places. So that means that this one is gonna give you 7.30 times 10 to the power 3, and that's the final answer. That's how you work it out. And then we have got C. We have got 1.9. So for this guy here, the first thing is we are gonna start with what is on top. So we have got 1912 times 0.0077 multiplied by 10 to the power 4, and then times 3.12 times 10 to the power negative 3. So that has given me a 4.59 33888 times 10 to the power 2. And then we are dividing this in the denominator. You can see the number that we have. So we have got 4.180 times 10 power negative 4. It is raised to the power negative 3. Just write that number in brackets. Okay, as simple as that. So, but what I'm gonna do is this. Let me first do something and then I come back. 4.180 times 10 to the power negative 4, and then this answer is raised to the power 3. So the answer that it has given me is a very, very big number. Let me look at it in standard form. Okay, so this answer in standard form, why is it not even giving me? Aha, 6.289,329,6977 times 10 to the power 12. Okay, let me now do what I wanted to do. So in the denominator, just put in brackets there 4.18 times 10 to the power negative 3, and then raise that answer. Oh, sorry, it's times 10 to the power negative 4, isn't it? Negative 4. And then raise that answer to the power 3. So that has given me a 7.303 times 10 to the power negative 11. Okay, so that's what you do. You know, what you can do is now just get what's on top and then divide by what is down here. That is what is going to give you the answer that I've already written. But what you need to know for for division and multiplication, the rule is different. So after division or multiplication, the final answer is written to smallest number of significant figures. So it's no longer about decimal places, but about significant figures. So that's what you need to know. So meaning that for our specific question here, you need to know the numbers that we have and how many significant figures they have. Let's look at them. So for the first one, this guy has got how many significant figures? The one that I've labeled. Anyone? This one. How many significant figures does it have? Okay, very good. Excellent. And then how about this one? How many significant figures? 2. Very good. Okay. And then how about this one? How many? 3. Very good. And then the one in the denominator, how many? It's also 3, isn't it? It's 4.18. So the final answer therefore should be written. The lowest number of significant figures is just a 2. So the final answer should be written to 2 significant figures. So we should end here on 8, but to remove a 1 from 9. So that is going to give you 6.29 times 10 to the power 12. That's the final answer. Okay, written to 2 significant figures. Oh, sorry. What I've just written is the 3 significant figures. Okay. So 2 significant figures, means we are going to be ending on a 2. So this is supposed to be 6.3 times 10 to the power 12. Is that okay? Okay, very good. That is how we go about this question. The next question is saying, which of the following is the greater 3245 micrograms or 0.0515 milligrams? Now, for you to find which one is greater, you need to write them to the same unit. Okay, you people be telling me, should I convert microgram to a milligram or milligram to microgram? Okay, milli to micro. Okay, so we're gonna get 0.005. This is milligrams. We'll convert it to micrograms. So the way you do is you multiply. You can see I've got a milli on top. I'm gonna put a milli down. And then I'll first go to grams. Now a gram is bigger than a milligram. Okay? So because a gram is bigger, put a 1 in front of a bigger unit. Milli means to the power 3. 10 to the, so I'll write 10 to the power 3. It actually means a negative 3. But because I'll put a 1 in front of a bigger unit, always use a positive power. So this milligram will cancel with this milligram. And then I'll further multiply and now convert a gram to a microgram. Again, there's a gram on top. I'm going to put a gram down so that they can cancel out. And then I'm going to a microgram. Micro and gram, which one is bigger? A gram is bigger. Okay. Micro means 10 to the power 6. It actually means negative 6, but because I'll put a 1 in front of the bigger unit, always use a positive power. So this gram will cancel with that gram. So what you notice here is that the 10 to the power 3 can cancel the 10 to the power 6, will remain with the 10 to the power 3, which is 1,000. That 1,000 will multiply with the 0.0051, so the decimal point will move 3 times, 1, 2, 3. So the answer is going to be a 5.15 micrograms. So we are now comparing. This is the answer in micrograms. Okay, with a 324 micrograms. So which one do you think is a bigger unit? Which one is a bigger number between 324 micrograms and 5.15 micrograms? Anyone? So therefore 324 with a 5 there, 3245 micrograms is bigger. Okay, because the other one which is in micrograms is just a 5.15. Does that make sense? There's no one reacting and there's no one answering. Are we okay? Yes, please. Okay. So what I want you to know is this. When you have got a unit, where do I even write this? Okay, I'm going to write here. We are going to have a reference unit. I'm going to put a 1 here. On top, we are going to be moving in positives. We have got 10 to the power 1, 10 to the power 2, and then we start moving in multiples of 3. 10 to the power 3, 10 to the power 6, 10 to the power 9. I'll end at 12 because that's where we pay attention to. Down here, I'll use the same powers, but I'll attach a negative 10 to the power negative 1, 10 to the power negative 2, 10 to the power negative 3, 10 to the power negative 6, 10 to the power negative 9, okay, and 10 to the power negative 12. Now 1 is a reference unit. This one is a reference. It can either be a gram, can either be a meter, can be a second. Okay, think of any unit that is a reference. It doesn't have any prefix. A prefix is a term that comes in front. Now going to the up, 10 to the power 1, we call it a deca, and that's the capital D, because those have got positive power, so they carry capital letters. 10 to the power 2 is known as a hectare or hecto, capital H. 10 to the power 3 is a kilo, that is capital K. 10 to the power 6 is that's a million, is a mega. 10 to the power 9 is a billion, that is a giga. 10 to the power 12, that is a trillion, that is a tera. Okay, that is for the positive units. Going to the negative one, 10 to the power negative 1 is known as a deci, so it's a small d. 10 to the power negative 2 is a cent, that is small c. 10 to the power negative 3, that is a milli, that is small m. 10 to the power negative 6, that's a micro. But because we already have small m, we don't use also small m. Instead, we use nu, that's a symbol. 10 to the power negative 9, that's a nano, it's a small n. 10 to the power negative 12, we call that as a pico, that's a small p. So these are the reference, this is what you use. Okay, so now let's compare what we have here. Okay, let me work out first C, because it's the one that you need to use these units. Question C, we want to compare 3,257 micrograms and 0.000475 kg. Which one is bigger? So now you tell me, should I convert a kg to microgram or microgram to kg? Which one should I do? Okay, microgram to kg. So we're gonna get 3, 2, 5, 7 micrograms. We're gonna multiply. Okay, like that. We have a microgram on top. We'll put a microgram down so that they can cancel. The first thing that you do is first go to the reference units. So the reference unit for mass is a gram. What do I mean by reference? It doesn't have any prefix. There is no number, there's no letter in front. There's no kilo, there's no micro, there's no whatsoever in front. So first go to the reference. Okay? Now, because a micro is down and then a gram, which is the reference, is on top, that means that a gram is bigger. Anything that is on top means that it is bigger. So a gram is bigger than a micro. So a gram is bigger. So I'm going to put a 1 in front of a bigger unit. Now remember me, so this is milli. Milli means 10 to the power negative 3. But I told you that as long as I put a 1 in front of a bigger unit, just use a positive power. It doesn't matter whether you are using those with negative powers or those with positive powers. So this is gonna a milligram will cancel with a milligram. And then now we can convert to a kg because this is now in grams. So I've got a gram on top, I'm gonna put a gram down, and then I'm going to go to a kilogram. You can see kilo is here, gram is here. A kilo is bigger because it's on top. So I'll put a 1 in front of a kilo. And kilo means 10 to the power 3. So I'm gonna write a 10 to the power 3 where a gram is. Okay? Just remember to put a 1 in front of the bigger unit and then just get a power or the 10 to the power whatsoever and then put it on the other one that has remained. This gram is going to cancel with this gram. So you see, what you are going to have here is you have got 10 to the power 3 times 10 to the power 3 in the denominator. Okay? That is going to give you 10 to the power 6. And that will mean you have got 10 to the power 6, which is a million, divided into 3,257. So what is that gonna give? So the decimal point is gonna move 6 times. 1, 2, 3, 4, 5, 6. So there'll be 0 here, 0 here, and a 0 here. So the answer therefore is gonna be a 0.003257 kg. So we have converted to kgs. Okay. I hope that makes sense. So we have converted to kg. So look, the number that this number is 0.00. It has got three zeros. It has got four zeros in front. The one that you have found has got three zeros in front. So meaning that the one that we have found is actually a bigger number. So we'll say therefore 3257 milligrams is bigger. Is this okay? Are we okay, guys? Okay, let's go to B now. I didn't want to answer B direct. I was sure. Okay, don't worry. You're going to understand with the other practice questions. Okay, please just stick around. You'll be able to understand. Okay, let's convert the liters to. Okay, we have got centimeters cubed, and then we have got a guy that is in liters. So, which one should I convert to the other one? Anyone? Should I convert a liter to a centimeter cubed or a centimeter cubed to a liter? What should I do? Okay. So for this one, the only tricky thing is you just need to know the conversion factor. You just need to know that 1 liter is equal to 1000 cubic centimeters. That's the meaning. 1000 cubic centimeters. I've written to the power 3, that is a 1000. Okay. Someone might think otherwise. Let me just write 1000 so that you don't lie for me. So 1000 cubic centimeters. So we're gonna let's convert to liters. So get the 981 centimeters cubed. Or multiply. We have got a centimeters cubed on top. We'll put a centimeters cubed down. And then we'll put a liter on top. And already from the conversion factor, 1 liter is 1000 cubic centimeters. So this cancels with that. So 1000 into 981, that is basically 0.981. This is in liters. So this tells you therefore that the same 981 cubic centimeters is the one that is bigger, because 0.98 is bigger than 0.25. Does that make sense? Is that okay? Yes, please. Very good. Please, in case you are not fine, feel free to ask. Okay. And then we have got this one, 105 degrees Celsius to 373 Kelvin. So you tell me again, should I convert a Kelvin to degrees or degrees to Kelvin? You just need to know this. Okay, thank you. So the temperature in Kelvin is basically the temperature in degrees plus 273. For some, it will tell you 273. For others, it will tell you 273.15. You can choose. Okay, 273.15 is a bit uh, more accurate. So therefore, let's convert 105. 105 degrees, which is a temperature in degrees. When you want to take it to Kelvin, is gonna become that temperature in degrees, okay, which is the 103 in this case. Oh, sorry, it's 105 plus 273.15. So 105 plus 273.15, that has given us 378.15, and this is in Kelvin. So you see that one is 373, this one is 378. So we'll say therefore 105 degrees Celsius is bigger. Does this make sense? Okay, thank you very much. So these things are very easy. Okay, please switch off the mic. The next question, question 3 says, the beakers shown below have different precisions. Alright? Label the amount of water in each of the three beakers to the correct number of significant figures. Now you can see the first beaker, let's call this one as A, let's call this one as B, let's call this one as C. So can you see that the first beaker is moving in ones? 26, 27, 28. So for beaker A, the water is between 26 and 27. So that is gonna be a 26.5. Okay. And then for the second one, beaker B is moving in tens. We have got 20, 30, 40. And this reading is between 20 and 30. So that reading is actually a 25. And then beaker C, that one is gonna be, so for beaker C, we are moving in point ones. We have got 26.4, 26.5, 26.6. Okay? And look at where the water is. Okay? So if we were on the middle is somewhere here. Look at that. The middle would have been somewhere here. So could we have found the middle? So if you want to find the middle, which is here, you could have just said what is the on the middle between 26.4 and 26.5. That is definitely a 26.45. Okay, that's a middle. But now where our reading is actually the middle of the middle. So it is a number between 26.4 and 26.45. So what is that? What is that reading gonna be? That is that one. Yes, please. Okay, 26.43. Okay, that's a very good try. Okay, it's a very good try. So there. So in case you don't know how to find it, uh-huh, very good. 425. So what you do is just get this one, add to this one, and then divide by 2. Just that. Okay. So it's gonna be 26.45 plus 26.4 and then divided by 2. I hope that does that make sense? Okay, very good. You add the one that's on top with the one that is down and then you divide by 2. Okay, so that is a 26.425. So those are the values. The next question says, is it possible for each of the three beakers to contain the exact same amount of water? If no, why not? If yes, did you report the volumes as the same in part A? Explain. This is a very interesting question. So, is it possible for each of the three beakers to contain the exact same amount of water? Anyone who can answer that? There is one beaker where the measurements are happening in tens. The other one is happening in point fives. The other one is happening in point ones. So is it possible to have the same amount of water in all these three beakers? Why not? Hmm. Okay, they've got a different range of reading. So the thing is, this is possible. Okay, you can have the same amount of water, but the tricky thing is that the way you are reading, look at this. The amount of water can be literally the same. You can measure the water from, let's say, you use a different cup. You go and pour in each one of these. It's the same amount of water. That's the same. So is it possible for the three beakers to contain the exact same amount of water? Yes, it is possible. But what will make you to read different things is basically errors. We call them errors in reading. Where are those errors coming from? We call them random errors. They are part of the, it's because of the calibration of the instrument. We cannot do away with. Okay? So is it possible for each of the three beakers to contain the same exact amount of water? Yes. The second part says, if yes, did you report the volumes as the same in part A? No, we didn't report the volumes as the same. You can see one is at 26.5, the other one is at 25, the other one is at 26.425. But why are those different? Okay, why are the readings different? So I'm going to answer the second question. So is it possible? Yes. If yes, did you report those volumes? So say the volumes were reported differently, and the reason is because of the calibration of the instrument. Okay, because each beaker can only allow a certain error. Okay, because each beaker can only permit reading in certain points. Okay, so basically permit some errors which results in differences. I hope you've gotten it. You can always write this in your own English. Okay? So this is my English. You can use your own English. Stay away from loving Google. Okay? Stay away from loving those things. I've not gone through this paper before. This is the first time we are doing it together. And we're answering together. And we can answer like this, meaning that you can also do it alone wherever you are without using Google. Any questions? Yes, sir. Suppose what? it will still have been the same. It's the same explanation as long as the beakers that you are using don't really have they have got the differences in the points. Okay, the points you definitely find a difference in the reading, and it doesn't mean that the answer is wrong. Even if you bring a professional, they also find a different reading. Like you can bring three professionals to come and read just the volume of one of these beakers. Even this same one that I read, this B, I've read it as 25, but you can even see yourself. It is not exactly on the middle, because the middle is going to be somewhere here. It is likely on top of the middle. Okay? So if I was doing even good readings, I should have said this is actually a 26 instead of it being a 25, because it is slightly on top. But you can see I can't read B in points. I can only read in 21, 22, 23, 24, 25 because it doesn't permit for me to read in points. So from 20 to 30, there's no permission for me to read in points. But I've been given for A 26 and 27. Okay, there I've got a chance for me to read in points because between 26 and 27, I know that I'm gonna have a point. I hope that makes sense. Guys, switch off your microphones, please. Is that okay? Okay. The next question says, where are our microphones on? All right. So the next question is saying, suppose you pour the water from these three beakers into one container. What will be the volume in the container reported to the correct number of significant figures? Now, this is basically you understanding. If you pour, pouring is what? Is addition. Okay? So if you pour, you are going to add the volumes. Add. So let's add those values that we have found. The first value that we have found is a 26.5. So this is gonna be 26.5. Second one is just a 26. The third one is a 26.425. Okay, let's see, sum up these values. So 26.5 plus 26 plus 26.425, and that gives us a 78.925. But guys, remember, when you are reporting after addition, report to smallest decimal places. Okay, so the first number has got one decimal place. The second number has got 0 decimal places. The third has got 3 decimal places. So the final answer should have a 0 decimal place. So therefore, the final answer that we are going to report is going to be this 78.925 is going to be basically 79. That's what you are going to report. Does that make sense? Is this okay? Very good. Okay. So that is basically that happens. We are gonna, I want us to continue. Okay, let's just do question 4. We have gone into the time for got a class with the third years or the fourth years. So to determine the volume of the sodium hydroxide, 3 students Cleopatra, Joshua, Eugene made a set of measurements with a burette from 3 trial titrations as in the table. Okay? So for these things that have been given, let's first find the average. I'm going to put a table for the average. Alright? So let's start with Cleopatra. So we're going to add the values and divide by 3. So I've got 17.23 plus 17.21 plus 17.26, and then divide that by 3. That has given a 17.233. We go to the second person, Joshua. 18.21 plus 17.61 plus 15.42 divided by 3. That's 17.077. We go to Eugene. 15.64 plus 15.61 plus 15.63, and then divide that by 3. That is gonna be a 15.527. And then for Natasha, 16.31 plus 16.37 plus 16.34, and then divide by 3. That is a 16.34. Okay, now that we have got these values, the first question says if the true volume needed to complete the reaction is 15.62, okay, which of the students would illustrate the following? Imprecise and inaccurate. Now, to be imprecise means that the values that are repeated measurements are not close to each other. Okay, so let me just first mention this. Precision, how close repeated measurements are. Repeated measurements are to each other. And then when you talk about accuracy, it's about how close the average is to the true value. How close the mean value is to the true value. Okay, the true value. So we want what is imprecise. We want those measurements that are not close to each other. So for Cleopatra, you can see 17.23, 17.21, 26. Those are close to each other. They only differ with the last digit. Joshua 18.21, 17.6, 15. This guy is a very bad boy. This is the one who is wasting our equipment at UNZA. He goes in the lab, is doing a titration just like you guys will be wasting these things when you start doing. How can you be finding those differences? Okay, so this guy is not precise because the repeated measurements are away from each other. And then Eugene 15.64, 15.61, 15.63. So this guy is precise. Natasha is also precise because only the fourth digit is different. So Joshua is imprecise because the repeated measurements are not close to each other. It is also inaccurate because the average, which is 17.07, is very far away from the mean, which is 15.62. Okay, so therefore Joshua is both not precise and not accurate. For 2, precise but not accurate. So precise means that the data, the measurements are close to each other. But it's not accurate because the average is not near the true value. Let's say, for example, the true value is 15.6. You can see, okay, 15.6. Cleopatra measured 17.23, 17.21, 17.26. Those values are close to each other, but they are very far away from the true value. So Cleopatra is precise because the values repeatedly are the same, but is not accurate because when you compare the average of the values that Cleopatra was finding with the true value, they are very far away from each other. Okay, I hope that makes sense. And that's actually the same with this girl Natasha. So if the true volume needed to be that, which of the students would illustrate the following? So Natasha is also 16.3, 16.3, 16, but the true value is 15.62. So Natasha is also going to be put in the same category. She was finding similar values, but then they were not close to the very close to the true one. You see, simply because you are doing the right thing doesn't mean you are finding the true thing. And this is why many students fail natural sciences, NS, because they think I'm studying. But the thing is not about studying. What are you studying? That is the important thing. You can be so consistent in studying, just like this Cleopatra. She's consistent in finding the right values, but she's not getting the right answer. She's consistent and she's getting the true things, but she's not getting what she's supposed to get. And probably some of you might be working like this. You are consistent in studying. The library you visit it for real. You go there. We can't lie. But then you are just missing it somewhere and you can't pass. Why? You are precise, but you are not accurate. So being accurate means that you know I am studying, but what exactly must I study? Okay? Because it's not about studying. Some of you come to the School of Medicine and you'll be studying. Just the first year in the School of Medicine, you go back home. Because you were studying, but you were not accurate. You were precise. That is why you got to have people around you that are going to mentor you and tell you what exactly should you study. I always tell my people, I can teach you for a week and I can assure you will not fail. Okay, I was teaching someone didn't do well in 2 courses, and this is in medicine, and then they were crying. I don't know what to do. I have done bad in 2 courses and I'm writing a supplemental exam. I told them, don't worry, come here. I'm going to take you into those two. And then they were talking to other people to say, passing in medicine. And actually, at third year, you can't pass 2 courses. Writing a SAP in 2 courses is not possible. I told the girl, just come here. Let me give you the data. And guess what? There, she's made it. She's now a fourth year. Because I was giving her the accurate data, not just precise. And that was in 2 weeks' time. Okay, 2 weeks' time. The medicine that someone was supposed to learn the entire year. So it is being accurate. That's why you need to have people around you that are accurate. Alright, we'll not go much there. The third one is saying precise and accurate. So precise and accurate. Precise means the values are repeated and they're close to each other. Accurate means the average is close to the mean, to the true value. So you can see for Eugene, 15.5 is not too far from 15.62. So that is accurate. And then the values themselves are also close to each other. In other words, every time you are accurate, just know that you are also precise. because you can't be accurate but you're not precise, but you can be precise but you're not accurate. So Eugene is the guy. Okay, be like Eugene. And then B, we should be the, oh, it's not the last one, we have got two more. Give a possible explanation as to why data can be imprecise or inaccurate. So when you talk about precision, the problem can be a fault in the instrument. Okay? Fault in the instrument. Let's say, for example, this instrument is like this. Here it is showing 2, here it is showing 5, and then here it is showing 3. Okay? Like this. If you come, okay, let me put, yeah, okay, just even like this. If you find water that is reaching up to here, you come and read. What is the answer you are going to give? Anyone? What answer are you going to give? What is the volume of that water? Okay, someone can say 5.7, 5.5, and such. And it doesn't matter who you bring, they all find the same value, which is very wrong. Okay? Not because they don't know how to read, but it's because there's a problem in the instrument. Because if this is a 2, this is a 3 on top, it means that this should have been a 2.5, but it's showing a 5. So even everyone that comes to read, even if you bring an expert, they'll still find the problem because it is them. So we call these types of errors as systemic errors. And these errors, you can easily avoid them. Okay, they are avoidable. The systemic errors are avoidable. We also call them determinant errors because you can determine that, oh, this is actually what is wrong. This is what is causing this. For inaccuracy, really, this one might be a problem with the environment. Okay, environmental conditions that have changed. Environmental condition change. Okay. Let's say, for example, you are doing a titration, and then the environment has got windy. You can overshoot when you open the tap to do the titration. So these errors, we call them random errors. You can't avoid them. They are part of life. That is why even Eugene, who was precise and accurate, didn't find exactly 15.62. He found 15.5 because there is always a part of error in this life. However good I can try to be, I cannot reach to that extent. All I'm gonna try is to be a better person. Okay? All I'll try is to be a better person. And then, you see, he's saying, so these errors, you can't avoid them. They are unavoidable. What is wrong with saying a set of measurement is imprecise but accurate? I told you this is not possible because every time you are accurate, it means that you are imprecise. In other words, you can't have the average value being close to the true value, okay? But then the measurements that we are doing were not true. In other words, let me explain this. You cannot be passing, you cannot be consistent in getting good grades. Let's say you have got 70% as your final CA, your continuous assessment. It's not possible if you got, let's say, a 2%, a 4%, and then you got a, let's say, 7%. Okay, if there's an inconsistency in what you are doing, it's actually possible I can get a 2%, or I can get a 40%, and then I come and get a 60%, and then I'll still get good results. Okay, because you find the average. But generally, when the repeated measurements are not good, it will also mean you are not going to be accurate. Okay, but if the repeated measurements are good, it means you are also going to be accurate. So the better the repeated measurements, the better, the more accurate, the more accurate. So it's not possible for you to have accuracy, meaning that the value that you have found is close to the actual value if all the process was wrong. Okay? And I love that point I brought. So you can't be accurate if the process is wrong. Okay? That's a meaning if you say you are imprecise but you're accurate. It means that the process was wrong, but then at the end you are right. It's not possible, guys. It's not. So if at this point you start getting it wrong in NS, I can rest assure you, you have if you just miss the process right now, this is not to scare you, but unfortunately I can tell you can't pass. Okay? Because you've missed all the steps. How do you expect to get it later? But likely if you start well today with your NS, I can give you my word. Even if you become reluctant at the end, you definitely do it and you do it with good grades.